Like to introduce John Briand. John is a principal geotechnical engineer with 12 years of experience at CDM Smith here in Raleigh. He's a professional engineer in 7 states in the District of Columbia and works on projects throughout the Southeast and nationwide. John is responsible for supporting the design and construction of dams, levees, deep foundations, excavation support systems, retaining walls, bulkheads, and trenchless crossings for a variety of our water, wastewater, commercial, federal, and large civil works clients. He has a bachelor's degree in civil engineering from University of Massachusetts at Amherst and a master's degree in civil engineering with a geotechnical focus from Virginia Tech. So that I'd like to hand it off to John.
Thank you, Pat. Appreciate you guys for here today. Let me know if anybody can't hear me properly. Same thing with online. So today I'm going to be talking about horizontal directional drilling, going through some best practices and key considerations for the design and construction of HDD alignments. So for my agenda today, really just going to provide a general overview of horizontal directional drilling for those of you that may not be geotechnical or civil in nature, and then get into the contract document side of things with more of your conceptual level HDD evaluation information, really figuring out whether HDD is right for your project or not, and then getting into more of the detailed HDD design considerations, preparation of your plans, specifications, drawings, as well as pulling together your geotechnical program for the work. And then finally, I'll get into some HDD project case histories that'll show you some unique aspects of HDD. So for the overview, really HDD is a trenchless method as opposed to your typical tunneling methods, whether it's jack and bore, microtunneling, or other methods. You are actually launching this from the surface as opposed to from a trench box. And so you're using a drill string to excavate the tools under the ground. And so usually you need an offset, as you can see here from, we're going under a river on this one up in New Jersey. You need an offset from wherever you're going. And so as opposed to a vertical shaft that you typically have for most trenchless construction projects, you're having to do that offset in order to get underneath whatever you're crossing, whether it may be a wetland or river or other objects. And so for those of you not familiar with HDD, this kind of shows your typical profile. At either end, you have a pit that you'll be drilling to and from. So on the left side here is our HDD entry location or your rig side. And so that's where you start your pilot drill. And with your drill, typically you're going between about 8 and 14 to 16 degrees on your entry angle. And then you come through a vertical curve down at the bottom. Occasionally you get rid of this straight segment underneath wherever you're going and then come back out the other side on the pipe side. And so for that, you're typically wanting to do a predetermined bore path where you're figuring out how deep under whatever object you're going, whether it's a river, wetland, or utilities, prior to determining how long you need for your drill, because getting to that depth with those shallow angles is very important in the design of your HDD. So HDD is a multi-step process. So initially, you can see here on the top right, you have your pilot hole. So when you do your HDD, you may be looking at a pipe anywhere from 2 inches up to about 60 is about as big as HDD technologies go. And so in that initial drill, you're usually looking at a drill rod between about 2 and 8 inches in diameter. And so initially you're pushing out into your formation. And so it is a little bit harder from the steering aspect than some of the later passes. And so you drill out and you use what's called bentonite drilling fluid, which is basically clay that's suspended in water in order to take your cuttings from the head of that drill rig to get it out of the hole. But that also serves that, especially in soil profiles, to bring your cuttings back to the pit so that you don't get any clogging along the HDD alignment. So after that first pass, which is called the pilot hole, and you end up at your exit side here on the right, you do what is called the reaming passes. And so depending on your pipe size with the reaming passes, if you're going up to say a 36-inch diameter pipe, you'll probably need about a 48 to a 54-inch borehole. You cannot go from just an 8-inch pilot bit all the way up to a 54-inch final hole. And so you usually step those up in anywhere from 12 to 24-inch increments. And when you do your reaming pass, instead of pushing out the reaming pass all the way, similar to how you may push a straw into soil, you actually pull it back because it gives you more pull force from the rig. So you have your rig here on the left side, and all your remaining passes actually come from that exit side to the entry side. And then finally, for your actual pullback, what you do is you typically attach the reamer head right to the front of the HDD alignment. You attach what's called a swivel head that basically keeps the pipe from having any torsional forces on it. And then your pipe is attached to the back of that, and you pull that all the way back through in one pull. Occasionally, for longer HDDs, if you're looking at a couple thousand feet or you have some site restrictions, you may need to have some intermediate fuses, but if at all possible, you want to keep that one singular pipe fuse prior to your single pullback. So just a couple pictures of those different processes. So the pilot hole drill right here, you can see your HDD equipment with your drill rig, your drill rods, and your crews working on that side. For the reaming passes, you can see here these reamers. These are called barrel reamers, where you get the drilling mud coming through those reamers, and those are meant to enlarge the borehole. There are various different setups for whether you're doing soil and rock. And then finally, for your pullback, one of the more interesting things, and you can see your reamer here, you have your swivel head, but a lot of times, especially on these longer drills and larger pipes, you have to have various setups to actually stage the pipe. And contractors, it's typically up to their needs and methods, can get very creative with these things. Here you can see that they're using cranes with slings. Sometimes you'll have pipe rollers that you'll see in future slides for me, but they can get creative. Such I've seen where they've used actually shipping containers to get up and over various driveways or roadways. And so there are a lot of different ways that they can lay that pipe out. So just a summary of some of the equipment that you're using with HDD. So on the far left here with your pilot bit, that is your drill head. You can see at the bottom there with your bit down there, that's where the bentonite fluid comes out to push the soils back to the hole. You have to put in a little additional pressure into that in order to get those fluids moving. But once it starts moving, you should have a continuous operation. And then we use typically tracking drill heads, so you can see where it's placed right in that drill head bit from one of our projects. For those, usually you're using walkover units where they actually just walk along with those. But if you do get into some deeper drills through under rivers or things like that, they do have what's called gyroscopes that can actually send that back through the drill string instead of using a walkover unit. Here on the middle right here is a picture of one of the reamers from our projects that shows you the size. This one was a 48-inch ream for a 30-inch borehole. And then finally on the far right here, you've got your swivel right here that keeps you from getting those torsional forces on the pipe during the actual pull event. And then your final configuration here with our pipe laid out, and you can see the rollers that are more stationary and more typical of most HDD projects. And the purpose of that is so that you keep the pipe off the ground so that you don't get rocks that gouge it. Typically, we try and keep those gouges to less than 5% of the pipe thickness in order for the long-term operation of the pipe to not have any issues. So for your HDD side setup, so this is more of a large scale setup with a maxi rig. For this project, which I'll talk about later, it was about a 1,700-foot pole. So for the larger projects, your drill rig is going to have a crane that actually sits directly on the rig itself, as well as your drill pipe storage. For smaller projects where you're using a mini or a midi rig, you usually have about 10-foot long sticks. But for these maxi rigs, in order to optimize production, but also stay within DOT requirements, the drill pipes are about 30 feet long. You can see here on the right, you've got your mud pump that keeps it recirculating from the pit. So you're constantly recirculating the same material. You've got your soil separation plant over here, where basically once they're pumping out of the pit, they use a screening device in order to get the sands and clays and various soil or rock materials out, and then are able to recirculate so that you're not constantly bringing new water and mud into your site. And then you can see here they did have a vacuum excavation truck that is for potential frack out issues where you get drilling mud coming to the surface. But also, if you do have too much production, then you may have to use that and bring some of the additional mud off site, though we try our best to avoid those situations. So on the opposite side, you have your HDD pipe layout area. And so, like I mentioned before, you want to try your best to keep the pipe welded to a singular pipe string. But you can potentially have those intermediate pipe fuses. Additionally, you can see there that they have the pipe rollers strung out. And usually on the exit side, you also have a vacuum excavation truck. For shorter drills, you may only have one at the site, but this was a longer drill of about 1,500 feet. So they wanted to have the equipment available on both sides of the excavation. And then this picture here shows you for some of these mid-sized drills where you're not using larger rigs, a lot of times they'll just use the excavator bucket and the pit itself, instead of being shored like your typical jack and bore formation. Usually they're just excavating 3 or 4 feet deep with an excavator bucket and letting their drilling mud circulate on the exit side. And so from there, you can see that this is right before pullback, where you have your reamer ahead of here. This is your mud pit, and then you're pulling in. One thing on most projects that we have is tracer wire, and similar to your open cut environments for these plastic pipes, we'll usually include 2 sets of tracer wire on this, just because a lot of times it may get caught. We do usually have this is an older photo. We do have more robust tracer wire setups now that are less likely to have issues with pulling into the borehole during the construction. So getting into the conceptual level HDD evaluations, this is kind of your general planning to see if HDD is feasible for your project. So initially, we'll start off with our risk evaluation, doing a desktop study to identify issues associated with the project site. A lot of this has to do with areas for laydowns. HDD obviously is fairly difficult in urban environments where you're trying to lay out your pipe string. And so that's one of the things you want to check out to see whether HDD is works for your project. Additionally, we'll want to look for obstructions such as foundations. If we do have our plan and profiles, to figure out if there are any utilities that we need to go under, or other critical underground items that we're aware of before the construction, though sometimes you're figuring these out after you've started your HDD. In general, for your HDD evaluation, favorable for most soil types and rock types, HDD is favorable. Any sands, clays, silts, and consistent bedrock are all favorable, though obviously with bedrock versus sand and clay, you will have a much slower production rate. Unfavorable ground conditions that you may see is that you have obstructions around here. Obviously, with the partially weathered rock, you can get floating boulders and things like that. So you do need to take those into consideration for your HDD design. And then when you get into truly hard rocks, like you get over in the mountains and in the Appalachians, once you get above about 30 KSI or 30,000 PSI rock, HDD becomes a very difficult technology. It becomes extremely slow moving. And so a lot of times your tunneling methods like microtunneling or pipe jacking or hand mining end up being quicker than the HDD, and actually more cost effective for you. Additionally, for pipe sizes, like I mentioned before, I mean, you can go anywhere from about 1 inch to 60 inch. And when you are doing your design, you do want to consider those aspects. There's much more requirements that we look for in the contract documents with a 60-inch pipe compared to a 2 or 4 inch pipe. With your typical HDD that you're looking at for plastic pipes, you can typically go to about 7,500 feet in crossing length with fusible PVC pipe. HDPE pipes, they are getting better resins and specific pipe types, where rule of thumb is about 2,000 feet is where you're usually limited with standard HDPE pipe, but they are getting into the 3,000, 4,000 foot range with very specific polymers. Additionally, there are, for large drills that may be under intercoastal waterways in Florida or things like that, you can go over 10,000 feet with these drills now. And with those drills, you actually drill from either end and then you meet in the middle, and they have very advanced equipment to be able to have that sort of accuracy. Additionally, it allows you have pipe pushers that actually help the drill rigs, because the forces are so great that an individual drill rig can actually push the HDD in there. Like I mentioned, for pipe types, you're usually looking at your HDPE, fusible PVC are the 2 primary items. But for those longer drills, you do end up getting into steel. And then there are restrained joint type setups, where we did one in West Cary with ductile iron, where you can actually use both ductile iron and restrained joint PVC in some more urban areas where you prefer HDD, but you might have issues with stringing pipes out, though those are more limited. And then finally, you kind of want to look at your easement areas, whether it's your entry and exit points, your pipe laydown areas, and then generally if you have any horizontal constraints. And so all those are part of our initial conceptual evaluations. So getting into detailed HDD design, this is really going from your 30% to 100% designs. Your first item that you're doing is you're selecting your horizontal alternative. So do you have bends in your roadways that necessitate horizontal curves? We would prefer to keep our alignment straight, but obviously with infrastructure and urban environments, as well as other things in ports like piers and the such, you do need to figure out exactly what your optimal alignment is. Then the second step, which is really important, is conducting your investigation program. One thing you need to consider is you are usually drilling under a wetland or a river, and you do need to go much deeper than the actual channel. So if your channel is 40 feet deep, you might have to take your borings to 100 feet. Additionally, you usually have a general idea about what the subsurface conditions are, whether it's rock in the Appalachia areas, in the Piedmont, you're looking at PWR and rock, and then out by the coast, you might get outcroppings of limestones and things like that. And so it's very important to know what your investigation program is. Typically, we try and get boring spaced every 500 to 1,000 feet, depending on the length of the alignment. And then the next critical step is your subsurface profile development. So for that, a lot of times you're going under really poor soils like soft clays that you can see here in the green, but that's obviously a little small for you. And so in order to avoid frack out, which is basically the drilling mud because of the differential in head going from the borehole up to that mud line, you need to seat your HDD deep enough in order to avoid that situation. If you do have a frack out, these things can be healed. They'll stop the drill, let it heal for a little bit, the bentonite will swell up, and most of the time you're okay. But if you do get large enough frack outs, it prevents you from continuing your HDD because the hole is too wide and your drilling mud just will continue to go to the surface. And so you cannot pass that point and keep the hole open the rest of the alignment. So that is a key portion of your design, especially for the longer drills that you're looking at in some of these poor soil areas. So the next step, like I had just mentioned, was really doing your frack out design. So on the left here, we use a product called Sigma W, but there's spreadsheet methods and many other methods to evaluate that. What you're looking at is the pressure of the drill that includes both that pressure head from the start and end of your alignment down to the borehole. That could be on the order of anywhere from 20 to 50 to 100 feet, depending on what you're crossing under, as well as that dynamic pressure in order to get those cuttings back and making sure that your soil has enough confinement and density to keep from having that frack out to the ground surface. I will note that the materials that you're typically using are biodegradable. So DEQ and other organizations prefer not to have these things happen, but it's not like you're emitting any dangerous substances to the environment. Though depending on your state regulatory agency, some are a little bit more stringent than others. And then finally, once we perform that frack out, we can determine how deep under whatever water body or utility we need to go. And then we can establish our vertical profiles. From that, really the key things are your entry and exit angles, obviously being far enough away from whatever you're crossing under, whether it's utilities or the water body, as well as having the correct radii of curvature. So if you're drilling in rock, you're going to have a much shallower curvature that may push your HDD drill to be longer. Whereas if you're sands or clays and you're using plastic pipe, you can have pretty tight bend radiuses as tight as about 400 to 500 feet. And the one thing to note about that is when you're dealing with plastic pipe, the steel drill rods that are actually drilling the hole are what is setting your geometry for those curves, not the actual plastic pipe, because obviously the steel is not going to be able to bend at as tight of a radius. And then finally, for your pullback forces and pipe stresses, the last portion of this is once you have your alignment set, you make sure that the forces that you're pulling where you're getting drag from the drilling fluid within the borehole aren't going to exceed the pipe's capability. to resist those and so that the pipe won't pull apart. Obviously, on your shorter drills on the order of 1,500 feet or less, that's usually not a concern. But for your longer drills, you may need to change pipe materials based upon that, as well as the dimension ratio of the pipe plays a key role. Because if you are getting close on those pull forces, you can look at thickening that pipe wall, though obviously that has cost implications. So from the development of the contract drawing side of things, these recommendations are a little bit more for your larger scale HDD projects. If you are doing smaller HDDs, you don't have to go to as great of an extent of documenting the areas for the contractor. But for our larger projects, what you do want to do is you want to obviously make sure your vertical and horizontal alignments are on the contract drawings. We'll specify what our HDD entry and exit angles are. Ultimately, for larger projects, especially because this is a lot means and methods based for the contractor about what their final drill tooling is, what their mud pressures are that they're going to be using for the drills. We make our assumptions during the design. And so ultimately in the specifications that I'll talk about, some of these things may be tweaked by the contractors. And I would say in general, we see maybe between about a 30 to 40% of our drills, the contractors will make tweaks to the final alignment based upon their equipment. And so typically we like to show those entry and exit angles. We do always want to specify that minimum radius of curvature to make sure that they aren't causing issues with the pipe itself. One of the big items is delineating temporary easements. If you do not show an adequate area for the contractor on the contract drawings, then that can cause issues during construction with having the available space to actually install the pipes. For your HDD entry side, it is when you're using maxi rigs, we usually use a rule of thumb of about 150 by 100 feet for our temporary areas, because as you could see in that previous image, there is a lot of equipment that you do need to store and move around at the site. And on the exit side, because you don't have as much equipment, you have you might have an excavator, a vacuum truck, and then the pipe materials there. We're typically looking at about a 50 by 50 area is what we typically look for some of these larger drills, as well as obviously the laydown area for the pipe itself. Additionally, one consideration in more of your wetlands and coastal environments is if you do have those very poor soils where you may get significant frac outs and movement of the mud directly adjacent to the either the entry or the exit points. Sometimes what we do is we install a larger steel casing where they actually drill through that casing, and it might extend to about 50 feet below grade in order to contain that mud and avoid having issues with keeping that hole open. Our additional information will include on there are test borings as well as utilities and obstructions and your wetland boundaries. And so those are the main items that we'll make sure to include in our contract documents. On the specification side of things, the qualifications is typically for your larger scale projects, especially when you're getting over a couple thousand feet. You want to make sure that the contractors are actually able to do the work. And your regional contractors may say that they might be able to actually do that drill, but you can run into a lot of complications during construction. And so for those larger jobs, we really try to make sure that they have those, whether it's pre-qualifications or just minimum requirements in the specification. One of the ways, in addition to thickening the pipe in order to get a further length of installation without having to go to a different pipe type, is ballasting the pipe, which basically means that during the drill, you end up pumping water into the pipe below grade in order to balance it in the hole. And so instead of the pipe dragging along the soil at the top of the alignment, you end up, the pipe seats itself in the middle, and you get a reduction of about 40 to 50% in those pullback forces that can actually allow you to take that same, say, HDPE pipe and pull it the entire length instead of having to go to fusible PVC or steel that may be more expensive. Besides that, we'll typically have them monitor your horizontal and vertical tolerances anywhere from about 2 to 5 feet plus or minus, depending on the environment that you're in. And then for your larger projects, there will be more detailed monitoring of the mud pressures that are coming back, the flow rates, what the fluid viscosity is for that pipe. Because if you designed it for 1.2 specific gravity and they're installing it at 1.7, then you could have problems with the pipe pulling apart during the drill. So then finally, we get to the construction side of things with the submittals. And in general, our best practices are for those larger jobs, getting the calculation packages from the contractor. So they, based upon their final means and methods and mud design, they will provide us their calculations that show that their proposed means and methods of construction are working. But again, for those smaller jobs where you're looking at a 500 to 1,000 feet, a lot of times we won't include that as a requirement because it's burdensome for the risk associated with the work. We also require them to have their HDD work plan. How are they doing the construction? What are your mud weights? What type of equipment? And our contingency plan. So frac out is usually the biggest contingency plan. Is what will you do from the environmental standpoint to close up those holes? Will you have vacuum excavation equipment on site? Will you have hay bales to contain? For water drills, making sure that they have booms on site that can contain that mud. And I'll show you one project where we actually had to use those. And then finally, for these larger projects, we do want to have risk mitigation meetings, making sure that everybody understands what the lines of communication are during construction. I think as civil engineers, we all know that sometimes those things can get confusing. And so for these larger, more complicated drills, making sure that we have those proper lines of communication. So if an issue comes up, we can address it right away instead of having arguments between the engineer and the contractor during construction about who can make the decisions. And so those are really the basic considerations behind how we approach developing contract documents. So now I'll get into a few case histories. So in general, I think a lot of people know that HDD is used for gas lines as well as water mains and sewer mains. Wanted to highlight this project that we did up by Niagara Falls in New York because it is unique, where we ended up doing a full-blown duct bank within a casing pipe. And so we ended up installing a 32-inch fusible PVC pipe under I-90 in Buffalo. As you can see in the lower right here, we had some difficult subsurface conditions where you had in that, can't really see the pink layer on here, but there is here there was about up to 22 feet of till, and then the dolomite bedrock. And so similar to talking above, the issues with the till that you experience are those floating boulders in there. And so we ended up doing this drill through the dolomite bedrock in order to avoid those issues. Obviously progressed a little bit slower than a soil drill, but it accomplished the task that we were looking for. And so actually going back here, so the way that we ended up doing it was you install the larger pipe with this casing pipe that was 32 inches. And I believe there were either 8 or 10 smaller conduits of about 3 to 4 inches that were housed within a casing spacer alignment. And so once those casing spacers were installed, we ended up grouting the annulus similar to what you would do with just a typical duct bank that you lay down. So for the design and construction considerations, really the detailed subsurface investigation to capture the bedrock was very important. Knowing how strong the bedrock is, as well as how abrasive it is, will help you determine whether how many times the contractors may have to change their equipment. That is one big area when you do drill through bedrock. You can get issues with change orders where contractors say that they don't have enough information to have designed their drill heads. And because those drill heads are using diamond bits and things like that, they can get pretty expensive when the contractor is putting those together. Additionally, like I mentioned, we had the contractor specifically design a casing spacer alignment in order to bring all of those singular pipes into there. And so you drill that first casing pipe, install that, and then we pulled all those pipes through and grouted those. And then here on the middle, in the bottom middle right here, just kind of shows you a typical cab setup where the contractor can monitor their drilling progress by drill rod. It shows you all the drilling fluid pressures and everything associated with their measurements. So really the critical success factors for this one is we did have a pre-construction meeting on site, and you can see how these casing spacers are set up right here on the alignment here. In order to discuss how we were going to be bundling these and how they were going to work through the rock. They did not have any major issues with getting through the rock. It was a little bit softer, though they did have occasionally a couple issues with chunks of rock ending up in there where they had to back out and drill back in. And that is part of the contingency plans that they submitted. So they didn't have any major issues associated with that. So the next project brings us more down to the southeast, more of a coastal plains type geology in Columbia, South Carolina. So for this one, this was a 1,600-foot wetlands crossing, as you can see, 30-inch fusible PVC. And it had difficult subsurface conditions where there was about 30 feet of loose sands with flow counts of less than 5. And so frac out was a major concern for us. But the issue that we had with going deeper than that to avoid that frac out was there was a really hard pan coastal deposits layer that was about 6 to 15 feet thick that encountered refusal when we were doing our split spoon sampling. And so we did have concerns during design about going through that layer. And so some of the design considerations we had is we did have a very detailed geotech investigation. One thing to note for this, because the wetlands was so difficult to get into, we ended up offsetting our borings about 200 feet from the actual alignment to get adequate information, but not have to spend an inordinate amount of the owner's money to actually get those borings right along the alignment. We did get a request for a change in the final alignment from the contractor where their engineer was concerned about that potential for frac out. And so during construction submittal process, they ended up submitting that they would drill through that into that lower layer to avoid those frac out issues. After about 4 different attempts, the contractor was not able to do it. And I don't know if I have, here we go. They weren't able to do it. And so you can see in this photo that layer was so hard that it actually took a piece of 4-inch thick steel out of the reamer. And so they ended up going back to our original alignment. And because we ended up having it on the contract drawings and going through this middle process and noting to them that we do have concerns with drilling through this layer, it didn't cost the owner anything from a change condition. Like we considered, there were concerns about frac out. So near the end of the alignment, we did get one singular frac out here. You can see the mud and the gray. They ended up building a berm of soil and got the excavator in there to contain that. And then that fracture was able to heal after about an hour of downtime, and they didn't have another frac out for the rest of the alignment. And so one of the keys there was we did have full-time oversight of this by one of our junior geotechnical engineers to ensure that things were moving along adequately, and they were able to address both the frac out and the hard drilling conditions fairly quickly. And so ultimately for this one, we did have a pre-construction kickoff meeting that gave those lines of communication that made sure that we only had about an hour or 2 of downtime when they had the issues with trying to drill through that layer. And that identification of that layer during the investigation was really key to saving the owner money from potential issues with change orders and differing site conditions. So the next project gets us more into Piedmont geology. This is a project that we did up in Brevard over in the foothills of the mountains. For this one, smaller pipe size, about 24-inch. The big issue that we had here was the subsurface conditions, where we had about 12 to 14 feet of loose alluvials. And then on the land side, we had denser residual soils and PWR. But within the river profile that I'll show you in a second, there was basically no alluvium, and it was directly over PWR. And so we had to take that into consideration. Because our big concern was within the PWR layers, you do get a lot of fracturing, and with that limited overburden cover, you could potentially get frac outs and potential loss of the hole from that perspective, as well as the environmental issues. So originally, because the rock was over 22 KSI strength, and we were looking at more local contractors doing the work because of the smaller size of the project, we did put in 2 bid options. One was to open cut the French Broad, and then the other one, to protect the owner, was a guaranteed HDD drill. And so when we do end up having issues with concerns about the potential for construction and change orders if this doesn't work, occasionally we'll go to, in certain towns like Cary as well as Durham, a lot of times for Trenchless, will require guaranteed drills where the contractor may put in a higher price, but they are required to finish the hole no matter how many attempts. And so for this one, the HDD ended up coming in much cheaper than the open cut, even with that guaranteed bore. And so that allowed us to take some of the risk out from the owner and ourselves with potential for change conditions and not being able to do the drill, but still allow the contractors to kind of push the envelope with things. And so similar to what I was talking about with the booms earlier, we did end up getting a frac out in the French Broad. And so the interesting thing about that was we made sure that that was in those contingency plans, and we included that in the specifications. And the contractor had them on site and was able to contain the spill within 10 minutes. And both the city as well as our project management team ended up getting a letter from DEQ that provided praise about the fact that they were able to instigate that quick and not have to have any issues environmentally downstream. So it does show you that even though these things do happen and could have some environmental impacts, there are ways to mitigate those that will please DEQ and other agencies. So this next project, again, going back to more coastal plains. So this is down in Suffolk, Virginia, right by Virginia Beach and Norfolk. So this one was about a 4,000 foot crossing underneath the Nansemond River, just at the mouth of the river. And so for this one, there were several unique conditions. So obviously being coastal, we had very poor soil conditions going about 64 feet down of either soft clays or very loose sands. And then you got into a little bit more of a medium dense sand a little bit further down before we abandoned our borings. One thing about this is because of this coastal environment, I believe the mud line was about 30 feet below the water level. And so you do get that significant change in drilling or change in pressure due to the changing grade. Additionally, we had 2 obstructions. And so I'll show you in a second that we ended up putting in 2 horizontal curves along the alignment. And so for this project, this is a little bit unique where we did end up putting in, see this in this photo, but right here at the entry pit, we did end up using a 50-foot long conductor casing. You can't see it because of the trench box here. And that helped us contain any frac outs, and we did not have any frac outs on this project. Additionally, with these river crossings, getting that detailed bathymetric survey so you know how deep that water is, as well as for any potential obstructions, is key and helped us significantly on this project. When you do get to these larger drills, a lot of times for tunneling, like micro tunneling and the more costly tunneling methods, you look at a baseline report where the owner establishes the subsurface conditions in order to share risk with the contractor so that you're not always arguing over differing site conditions, because especially on tunneling jobs, the cost of bringing that tunnel boring machine out to the site is significantly expensive, on the order of millions of dollars sometimes. And so switching those machines out when things are not adequate can become a timely and costly legal battle. And so we'll use geotechnical baseline reports to establish what the contractor will actually anticipate. And so because there was concern about elevated bid prices on this project, we ended up doing a baseline report for the contract. And you can see the baseline report down here in the bottom right that established those conditions. And from the bids, the winning bidder on this one, I believe, was Laney Construction out of Texas. They ended up letting the owner know that for this project, this actually reduced their bid because they were able to take out some of the risk and contingency that they would have otherwise had for dealing with issues along the drill. And then, as I discussed before, we also use that conductor casing at the entry and exit points due to those loose soils. And so this really does show you how the bathymetric survey helps. So this was our HDD alignment in the red. It's kind of stacked in three different alignments with match lines. But basically, we had an abandoned dock that we had to go around over here. There was a former fishing pier, and then there was a former roadway that went over this the bridge had been demoed. And there were abutment piles that were wood piles that were not sticking up above the mud line. And so when we did the bathymetric survey, they were able to see those pile studs, and we were able to avoid those. Ultimately, we may have been able to thread the needle around them, but it allowed us to come up with a more optimal alignment. And then, as I had mentioned, the baseline report helped lower those bid costs because it reduced contractor risk. So then this is last project to go over, one of the more highlight HDDs that I've worked on. So this project was outside of New York City. There's a former island called Governor's Island in New York Harbor, right across from Brooklyn and Staten Island. And this used to be a former Army fortification back in the American Revolution. And then Stayed that way until about the 1960s, where it became a Coast Guard base. Once the Coast Guard base ended up closing with some of the closures, the city of New York ended up buying it and making it a public park. And it has 52 historic buildings from the various fortifications and Coast Guard base that they've maintained as historic features. And the park ended up getting over, and I believe now it's over 1 million visitors per year come to this park. But at the time, the park did not have any potable water. And so they were actually barging in water to the park in order to serve the public. And so the city, because this was a critical water line, even though we did go through bedrock as well as glacial till, for redundancy, in order to avoid any issues with the shipping channel, because this is the main shipping channel through New York, they ended up requiring us to use a 24-inch steel casing pipe to house the 12-inch ductile iron main. And so because of that, we had some very difficult subsurface conditions. You have your fill on either side. There was a stiff clay and then some loose sands and silts, and you got into pretty significant thickness of glacial till, about 11 to 42 feet, and then schist bedrock, which is one of the harder rock materials that you can work with, which did cause some issues. Additionally, we had obstructions on both sides. You can see here on the Governor's Island side, we had to go under one of these piers over there. And then there was a bulkhead that went down about 15 feet on the Brooklyn side of the alignment. And so similar, because of the concerns, and I will say New York State probably has the most stringent DEQ in the country. Because any spill in New York would shut down the entire project, we ended up driving 50-inch, or I believe it was 50-inch conductor casing on both the entry side and exit sides that extended about 100 feet into the alignment. One of the major things that we did, and I'll show it on the next slide, is we did know that there was glacial till and we were going to have to go through it no matter what. The till was very thick, but we didn't want to have the entire alignment through that till, which wouldn't have had issues with frack out due to our concern about those boulders. And so we reduced the amount that the drill was actually going through the glacial till to get into that confident rock. We had a significant amount of contingency plans that the contractor had to submit should they hit boulders and have to abandon the hole. And so that helped us a lot, because we did have 2 boulders end up in the hole where they used downhole hammers in order to break those up and still continue the drill. And for these drills, especially in the schist rock, we did do extensive lab testing that included abrasivity testing, which is one of the keys in this material, as well as a lot of unconfined compressive strength testing and tensile testing for the contractor to design the drill and make sure their bits were adequate. And so really the main success factors here were that extensive rock testing program, where the contractor sized their equipment appropriately, brought the right equipment out to the site, and they were able to drill this with only having to replace the bit one time each go. As well as you can see here, this kind of hatched area here, this was the glacial till area that we went through. So we could have gone through that alignment, but we chose to avoid it just for the facet of those boulders. And so we were able to limit that and successfully get that drill completed without any major issues. So I'll open it up to any questions. Yes.
To avoid fracture. Design patients consideration or the contractor's responsibility?
So it is shared responsibility. So from the standpoint of design, really, you need to have a constructible design. So if, say, you had a 3,000-foot crossing and you're showing your contract drawings that the pipe's 10 feet below grade and it's automatically going to frack out, the contractor has a pretty good case there. There is the reason why we require signed and sealed submittals, especially on these larger projects, is that drilling mud and how heavy it is really plays into the majority of the design, or how it plays into how those pullback forces work, as well as how much frack out you could potentially get. And so for the majority of our projects that are over like 1,000 feet, we will require those signed and sealed submittals by the contractor. But for those smaller jobs that you're looking at a 500-foot drill and it's not overly risky, usually that's on us as the engineer. So
if the contractor follows all the design guidelines and specs, but the frack out occurs under somebody's house, I guess it's
that
design.
if you're showing a non-constructible design, it's not the most, like, it's not the easiest.
That was perfect analysis to do either on something.
Yes, correct. There are a lot of assumptions that go into this, and so on the majority of projects, I would say it is on the contractor, just because it's ultimately their means and methods. But the owner, depending on how adequate the design originally was, like if you're showing from point A to point B and nothing else in between, then you can come into issues with not showing enough information for the contractor to do the design. So it's kind of a balancing act from that standpoint. Yes. Yeah, so typically for tolerances, we're looking for anywhere from, for the more urban environments, more of a 2 to 3 foot delta. But if you're in the middle of nowhere, you can get up to 5 to 10 feet. So it really depends on the risk associated with the project. For the smaller drills, especially if you're using more regional contractors, they're going to use your walkover units that their accuracy may be on the order of a couple feet off, so 2 to 3 feet off. And so you're always going to have deviations from that original alignment. And so your specifications is really where you have to determine how far off, but yet they're never going to hit exactly along that alignment that you show. And a lot of times, like I mentioned, 30 to 40% of the time, the contractors will come in and say, I'd rather do this different alignment based upon my equipment that I'm bringing. Yes. And so that's where, especially in urban environments, you want to make sure those variants for the utilities are noted, and you're showing those minimum clearances there, so you don't have issues. Yes. So basically there is special ductile iron pipe that can be used for HDD that is restrained joint. So they individually pull the joints together. And it really is, it depends on the deflection of the joint. And so we did a project over in West Cary where it was about a 900-foot drill, about 40 feet deep, down a slope, and we were able to get that in without issue. And so really the bigger thing is you need a longer alignment similar to steel pipe just to accommodate those deflections in the pipe itself. And so those restrained joints can take a certain deflection. They could potentially, and so part of the reason why you put that reamer in front of that pipe pulling back is the reamer is the size of the hole, and so it should dislodge anything. But yes, because you do have those lips on those bells with a ductile iron pipe, it may behoove the contractor, instead of going with 12 inches of over ream, which is usually what you do for most plastic pipes, they may go to 18 or 24 inches to give themselves a little bit more play. So some of that is up to the means and methods, because we won't tell them how big the hole needs to be. We'll just tell them that they need to get the pipe through. Yes. 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 So that was part of the contingency plan, and that was submitted to DEQ so that they knew what those contingency plans were. And so basically, similar to a lot of geotechnical specs, it is performance based. And so depending on the agency, like North Carolina DEQ won't look into that, but Virginia DEQ did require a submittal of the HDD design before we were able to actually do the construction. Yes.
Example that kind of where there's wooden piles.
Yeah.
Well, wooden piles stop drill. Like
it wouldn't necessarily stop the drill. The goal for they could drill through it. It's not as great as one, it could potentially clog your drill head, causing issues. Two, they could potentially put like a rock bit or something on to get through it if they're having trouble with the main soil bit. But ultimately for us, we just wanted to avoid having any issues with a true obstruction.
See, like what kinds of obstruction will stop it?
Like
a steel pile.
Yes, mostly steel piles, steel mains, like concrete piles. Obviously, you could have issues. boulders, larger cobbles. Those are things that can stop drills. And so some of those things, when you're in really coastal environments with sands, contractor is going to have a little bit denser of a mud in order to keep the mud from just going into the formation. If you start getting into like cobbles, boulders, things like that, the void space may be too large and you'll just get all the drilling fluid flushing out of the hole. And so those are really, it's mostly boulders, cobbles, and more like man-made structures that are the issues.
So we have two questions online. One question is for the New York City HDD, the one photo showed coming up through a concrete slab or pavement. If so, can you minimize the size of the hole to minimize the amount of pavement removal and repair?
So typically for this, you wouldn't really minimize the hole. So this was the pilot bit, and the contractor was extremely accurate on this. They only missed the hole that's just marked out by about 2 feet. But they're going to need a mud pit in order to construct this. And so you'll need to have at least, especially for this drill being 2,200 feet, it's going to be at least a 5x5 area that they take out of the slab. Like this was kind of a dock pavement area, so it wasn't a major concern. But ultimately, at a minimum, even for your smaller drills, you're going to need a pit of at least a bucket or two width of an excavator and probably 4 or 5 feet long to contain that mud, or else the mud will just spread over the entire area. So no matter what, you need to have somewhat of a pit at that location.
Then the second question is, if a casing pipe is required on either side, do you ever leave the casing pipe in place after the drill?
For that, no, they will always pull that casing. I mean, there could be a location that they do that, but obviously the owner bears the cost of having a permanent casing in there. And so typically they'll pull it on the probably 8 to 10 jobs that I've done with conductor casings. They've always pulled it. Any other questions? Yes. Yes. So, yeah, so it was along a tangent. So we made sure whenever you're doing HDD, general rule of thumb is you want at least one pipe stick in before you start making a curve. You can do horizontal curves, and very experienced contractors can potentially do that. But in general, we want to separate our horizontal from our vertical curves, or horizontal from horizontal.
Thank you, John. Appreciate it.